Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ahmad Syahrir bin Muhammad Syahrir. ID number Gh23068 from Group 2. And I will be representing my group to explain about introduction of our case study 2, which is titled Troubleshooting Unexpected Drop in Heat Duty of a Shell and Tube Heat Exchanger. So first, let me introduce you to the fellow group members. The first one, we have Dijia Hui, Alicia Liu, Hazim Imran, and Qaida, and of course myself, Muhammad Ahmad Syahrir. So without further ado, let's get started with the presentation. Let's jump into our introduction. In chemical process industries, shell and tube heat exchangers are vital units used to control process temperatures for downstream stability, product specification, and plant safety. A prime example in our case is heat exchanger E203, which is specifically tasked with reducing a process stream's temperature from 95 to 45 degrees Celsius. This cooling phase is critical. The downstream storage tank possesses a strict maximum allowable inlet limit of 50 degrees Celsius, and exceeding this boundary presents clear operational risk. High thermal exposure can trigger product degradation, breaking, or off-specification batches, directly impacting product stability and quality. From a process safety perspective, elevated storage temperatures can breach safe vapor pressure thresholds, creating overpressure risk or escalating flammability hazards. Furthermore, unchecked thermal variances generate downstream process disruptions that put stress on auxiliary equipment and compromise overall plant reliability. So that's it for the introduction.
So next, I will proceed with the methodology, X-step troubleshooting process. So the first one is the problem identification, which we will define the exact deviation from the nominal baseline parameter and define the increase of the temperature in the process stream outlet. So the second one is information gathering. We will gather the relevant information such as the data of cooling water outlet temperature, pressure drop, and rough misalignment. The third one is the hypothesis formulation. So we will list all of the possible causes that cause the problem. And the fourth one is testing hypothesis, which will evaluate the validity of the formulated hypothesis by comparing them against the collected data. So the fifth one are the root cause identification, which we will use it to identify the factor responsible for the system failure and recommend the targeted action. So the sixth are solution implementation. It used to design the effective solution for the corrective maintenance procedure to solve the problem. And the seven are verification. We'll use it to verify the outlet temperature of the process stream that return to 45 degrees C. And the last one is documentation, which we will record the key step to share insight for the future reference.
So I'll be presenting the troubleshooting process and results. So step 1 is define the deviation, step 2 is the evidence. So what the DCS says, software / elementary. So problem statement process steam outlet declined from 45 Celsius to 65 Celsius over 5 days, exceeding safe limits below 50 Celsius. Misleading norms, hot inlet is steady at 95 Celsius, DCS flow and CW controlling report normal. DCS normal, pressure drops and CW needs more process size slightly increase. So secondly, what field operations found, physical evidence, physical check, minimal amount outlet discovered, partially checked parameter in the field. Bypass passage, physical bypass like felt, worn to touch, suggests bypassing. Instrumentation error, heavy mismatch between physical, local gauge, and DCS screen saves. Alright, now we're presenting step 3 and 4, hypothesis testing metrics. So the hypothesis, so we separate into 3 parts: hypothesis / proposed, process and field evidence completion, and validation status. Okay, so the first A, valve management, is confirmed partially. The throttle, manual CW valves, drops actual flow. Validation status, validation primary. So B, bypass line leak, bypass final warm, to touch, uncooled, process, fluid, start, circulate, validated primary. C, fouling and scaling. Down dosing pump, scaling on shell, high solids from reactors, which is fouling. High on validation status, highly probable. So next D is instrument error. So the process and field evidence comparison is local pressure gauge, degree of DCS, and validation is valid for secondary. Okay, so step 5, the root cause weighting and prioritization. So 50% of the fluid dynamic issues, immediate impact, partially closed manual valve, and bypassing line directly, 35% fouling and scaling, thermal insulator, and 50% is instrument drift, system blind spot. Okay, step 6 and step 7. Step 6, action plan. Step 7, interpretation. So target action taken. Valve realignment fully open. Manual CW valves. Isolate the wall and bypass. Chemical, clean. Executed and localized tube side, backswash, and CW shell side and descaling flush. Loop calibration. Took faulty transmitters offline and recalibrated back to field centers. And then post-verification metrics is that thermal restoration. We process outlet temperature successfully restored at the steady 45 baseline. The storage protection downstream. The storage protection downstream inlet safely dropped below 50% hazard threshold. And depth stability both processors cited CW name drops. Return to clean and original design. Okay, so finally, step 8, continuous preventive planning. So milestone 1, we checklist, which is daily. Enforce manuals of valve position, verification logs for field operators. Milestone 2, dosing audits weekly. Implement the M checks sheet on the CW chemical dosing pump. Milestone 3, filtration monthly. Clean reactors, discharge filters to prevent tube side solid carryover. Milestone 4, cross-check quarterly. Cross-reference DCS readings, the physical field gauges to isolate instrument drifts early.
So for discussion, question 1, the E203 shell and tube heat exchanger is experiencing a critical operational failure. The unit is showing a massive reduction in thermal efficiency, transitioning from a maintenance issue to a high priority safety risk. Okay, first we look at performance deficit. The primary performance metrics show a failure to meet the target outlet temperature of 45 degrees Celsius, as the process stream is currently sitting at 62 degrees Celsius. This temperature has climbed progressively over the last 5 days. As a result, the fluid is entering the downstream storage tank 12 Celsius above the maximum safe operating limit of 50 degrees Celsius, directly compromising plant safety protocols and product quality. Next, we look at operational evidence. Data verification confirms this is a physical performance degradation rather than a sensor drift. Applying Kern's models, a decreasing temperature differential across the process site confirms a genuine drop in total heat duty. Furthermore, the downstream storage tank is reacting to this excess heat, which independently verifies that the thermal issue is a physical reality. Next, we look at hydraulic root cause. Field investigations identified the primary hydraulic failure. A manual cooling water outflow valve is partially closed, creating a throttling limitation. More critically, a valve passage exists. Although the distributed control system DCS indicates the bypass valve is closed, the line is warm enough to be touched. This confirms that utility water is short-circuiting around the unit instead of passing through the tube bundle. And lastly, we look at structural fouling. Physical degradation of the exchange's boundary layers is occurring on both sides. On the shell side, increased solids from the upstream reactor have caused significant particulate fouling. On the tube side, maintenance logs confirm that the chemical dosing pump has been sporadic for the past month. In the absence of consistent anti-scaling treatment, mineral scaling has accumulated within the tubes. So in conclusion, the E203 is being throttled by a combination of hydraulic bottlenecks, fluid bypassing, and an insulating layer of scale and particulates. These factors have created excessive thermal resistance, as a manual valve adjustment is required immediately, and followed by a full bundle cleaning to restore safety margins and the operational baseline.
My name is Alicia Liu, and I will be continuing for discussion question 2 and question 3. So for question 2, to find out the actual reason of why the decrease in the heat transfer performance is first to collect operating data, because it directly reflects the heat transfer performance, fluid flow conditions, and equipment integrity. Next is to verify cooling water flow rate using DCS readings and independent field measurements, where we need to compare the new and old data to find out which part of it is having an abnormal measurement. Next is to analyze pressure drop data and heat transfer performance indicator, because an increase in the pressure drops indicates the accumulations of solid, also known as fouling and scaling. Next is to collect temperature measurement along bypass line and compare with the standard, because an abnormally high or abnormally low temperature indicates that there is a malfunction in that part of the bypass line. Last but not least is to compare critical measurement with independent field measurements to find out which part of it is having a problem. Next, for question 3, to differentiate between an actual process problem and a misleading DCS measurement is to compare DCS measurement with local field instruments, because the difference between two measurements suggests at least one of it is inaccurate. Next is to perform direct field observations, because sometimes a physical inspection shows important evidence that cannot be obtained from control system data alone. Next is to conduct instrument calibration and loop check testing. The calibration compares instrument readings against certified standards to determine their accuracy, while loop checks verify that signals are correctly transmitted from the field app device to the DCS. Last but not least is carry out historical trend analysis. If several related process variables change simultaneously in a physical consistent manner, a genuine process problem is more likely to have happened. On the other hand, if only a single instrument displays abnormal behavior while other related parameters remain unchanged, the issue may be due to an instrument faulty instead of an actual problem. Next, I will pass on to my teammate for the next part.
My name is Btk4224 My metric number is G2 Case2 and I'll continue my part. So, first priority is valve phase alignment and cooling water bypass leakage. The evidence is field observation directly report that one manual cooling water outlet valve is partially closed and the bypass line physically fails warm, even though the DCS indicates that the bypass valve is closed. This provides immediate observable proof of a hydraulic bottleneck and fluid bypassing. First priority is instrumentation error. There is a direct confirmed conflict in data because the local pressure gauge reading does not match the DCS pressure reading. Furthermore, the DCS indicates a normal cooling water flow rate despite the cooling water side pressure drop being lower than historical values. Third priority is fouling or scaling. The cooling water chemical dosing pump experienced intermittent operation during the previous month. The upstream reactor recently reported an increased solid content and the process side pressure drop is slightly higher than normal. It is ranked third because fouling builds up over time rather than causing sudden, localized valve warm. Next discussion. The first one is troubleshooting checklist and precision trace. Draft, eliminate an E-203 performance deviation diagnosis tray located directly in the control room and field station. Next, pre-calculated baseline performance trends. Develop a dedicated automated dashboard in the DCS that continuously trends live heat duty and the overall heat transfer coefficient against clean historical baselines. Next one, standard operating procedure for valve lineups. Revise the heat exchanger, startup and turn around SOPs to mandate a physical sign-off and take regulation of all manual block, outlet and bypass valve. Next, logbooks for auxiliary equipment interdependency. Integrate auxiliary equipment maintenance logs, specifically tracking chemical closing pump uptimes and upstream reactor solid strand into a shared digital operator logbook. The last one is calibrated field kit readiness. Maintain a designated, pre-calibrated troubleshooting toolkit in the control room containing a calibrated handheld IR thermal gun, a portable ultrasonic thermometer, and a master pressure gauge for rapid independent field validation.
So in conclusion, the problem is the process outlet temperature increased from 45 degrees C to 62 degrees C over 5 days, and this problem can be solved by using X-step troubleshooting process method. And the main problem is because the heat exchanger system. And when same problem occur in future, we can do the checklist, real-time heat exchanger performance dashboard, SOPs for the post-maintenance valve lines ups, digital notebook, and also the troubleshooting toolkits. That's all. Thank you.